I'm going to be very fast, but just to introduce the challenges that we have nowadays to model Pyroclastic density currents. It's one of these hazards that is pretty tricky to simulate, and I'm gonna explain why. So first, I'm sure all of you know what a Pyroclastic density current is. Um, Pretty hot mixture of gas and particles of different sizes that can be generated from different way. I'm going to show you that next. That is sloping down the volcano slopes at very high speed and destroying everything on its path. Um, so here I put some pictures of the two main ways of generating Pyroclastic density currents. You can have a dome collapse, so a lava dome that is popping up at the top of the volcano, and then at some point that is growing so much that it becomes unstable and collapsing. And I'm showing you here one example of dome collapse modeling at Merapi volcano that we're going to use today using Titan 2D with different pulses of collapse from the source that is generating some Pyroclastic density currents that is filling up the valleys on the southern flank of the volcano and inundating um, this area here. So it's pretty directed towards one particular path, right? And it's pretty different from the second type of generation mechanism that's going to be a column collapse, where you can get all the way from Vulcanian to subplinian or plinian column that's going to start to collapse from different reasons. And the collapse is going to generate Pyroclastic density currents, but this time the PDCs are going to go all around the volcano at 360 degrees, inundated the volcano slope. And for that, you can use a more complex model like PDAC here from University of Pisa in Italy that is showing an eruption at Mount Vesuvius from a column collapse and some PDCs generated from that collapse of the column at 360 degrees around the volcano. So in terms of generation mechanism, I mentioned the dome collapse and then the column collapse. You can also have an explosive dome that we call a lateral blast. Similar to what happened at Mount St. Helens 1980 or Besimiani in 1956. It's also directed towards one direction, but this time the initial momentum created by the lateral explosion is going to increase the mobility of the PDC that can reach further distance down the flank of the volcano. And the last type of generation mechanism is the fontaining at the vent. So it's more like a boiling over, right? When you don't really have a column or plume generated by the eruption, but it's mostly some passing passive degassing and explosion of low energy that's going to create some fontaining with some gas and pyroclast that's going to go over the crater rim and generate Pyroclastic density currents. That happen at several volcanoes, like in Colima, for example, 2015. And it's also generating some dense to dilute type of PDC. So talking about the different types of PDCs, so for a very long time, um, volcanologists differentiated two main types, right? So concentrated PDC, what we call pyroclastic flows in many publications, versus dilute PDCs, what people call surges most of the time. Or ash cloud surge, or dilute surge. It's different. The terminology is like all of it's pretty messy, right? But there was these two end members, right? Concentrated versus dilute, and that was mainly based on the deposits that they produce, right? So concentrated PDC are going to produce pretty polysorted, massive units of pretty coarse class, big blocks embedded into a finer grain matrix composed of ash and crystals. Um, And that contrasts with the deposits from dilute PDC that are mostly finer grain, pretty thin deposits, often laminated or cross-bedded, and where the sorting is a little bit better. That can be deposited not only inside the valleys but also on interfluves and plateaus. And then more recently, people have tried to propose some different conceptual model that is recognizing the fact that you don't have only two end members, but actually there's a whole spectrum of dynamics and solid concentration, and actually a single PDC can actually change its solid concentration with time, the same way as Lara are doing with the bulking and debulking process. And so this is one of these models here proposed by Lubo et al. 2020, where you can see on the top here that you got a whole range of particle concentration where PDCs can form, and the transport regime can go all the way from dilute to intermediate and dense. So we don't have only these two end members, right, dilute and dense, but now we introduce like this intermediate regime, and there is more like a gradient and a spectrum of different coupling regimes and flow fields where we're going to go all the way from like frictional contacts and collision dominated regime all the way to like drag dominated regime where the gas is actually playing a huge role. That also affect what we call the coupling. So the coupling will be the interaction between the gas and the particles. And you can see that when we have frictional and collisional regimes where we are mostly in the concentrated field of the PDC, we're going to get four-way coupling, which means that we have full coupling full interactions between the gas and the particles. The particles themselves are also interacting. And we're going to go from four ways to two ways to only one-way coupling, where mostly the gas is interacting with the small particles, and the particles got a negative control on the dynamics. And then below, you can see basically some cross sections from the two end members, the dense and the dilute PDC, with some vertical profile of velocity and particle concentration, and then illustrating also where you can find the different coupling regimes inside those different types of PDC, as well as their vertical structure, where, for example, the dense PDC will have a basal concentrated layer that is pretty thick, right? And there's going to be some substrate entrainment at the base. And then the dilute PDC is lacking this basal underflow, and we'll have more like a bed load region that is pretty thin at the base that interact with the substrate. So all to say that PDCs are pretty complex, right? I mean, they're pretty complex volcanic processes that is going to create a lot of challenges for numerical modeling. So we're going to have to simplify somehow all these concepts, because we're not able right now to have a model that can take into account everything that I just talked about. So having like millions of particles, a gas phase, take into account the coupling, so the different coupling regimes, as well as a bed load, and then having all these over, a DEM complex topography will be computationally very, very intense and almost impossible to simulate. So that's why we need to do some simplification, and that's where the models are actually coming pretty handy, where you can still do some simplification without removing the main equations that are actually governing the dynamics of the PDC. So you see the table showing you some of the PDC models available nowadays. So you can see there's different approaches. You can go all the way from like just statistical correlation, so just taking some data from past PDC and then making that a model by looking at some relationship between area and volume, or between runout and area, etc. So the energy cone model was developed in the 80s and is still used nowadays for a very fast approximation of where the PDC can go, just based on the relationship between H over L, right? So the vertical drop divided by the horizontal distance of past PDC, and you relate that to the volume, and then you get this relationship for the energy cone line. LARZ has been modified to a code that we call PFZ, developed in 2009. That is exactly the same as a concept as LARZ. So we having a relationship between area and volume to actually compute how far a PDC can go inside a particular valley. And then we have some cellular automata models, some kinematic models, and then some depth average models. So that's the one we're going to focus here, because that's basically the one we have on Victor right now. Especially the kind of depth average models that are two-dimensional, transient, that involve a mixture of gas and solid particles that are incompressible. And then you have a last category here that is a multi-phase models that are three-dimensional, transient, and compressible, which means that the volume is actually changing during the propagation and emplacement of the PDC. So these models are pretty computationally intensive and pretty hard to actually implement on an online platform like Victor, but they are pretty good for getting some new information about the dynamics of the PDC and what's going on inside the PDC during transport and deposition. So the depth average models that we're going to talk about today are all based on the same governing equations. So what depth average means? It means that all the flow properties are going to be averaged on the vertical dimension, on the vertical axis, so on the direction perpendicular to the propagation. So we're going to average these properties, and then we're going to say, okay, we don't really care about what happened from the base to the top of the PDC. We care more about what happened, from the source to the end. And so for that, there's these conservation equations for mass and momentum that I actually put here, equations 3, 4, and 5. So equation 3 is just a conservation of mass. And then 4 and 5 are the equation for conservation of momentum in the x and y direction, right? So the two direction is going to be added to the flow propagation. And you can see in this momentum equation that you got a term here on the left side, and then you got another term on the right side. And it's basically just a balance of driving forces here on the left and resistive forces on the right. So if the term on the left is dominating the term on the right, then the PDC is accelerating. And if the term on the left is lower than the term on the right, then the PDC is decelerating and coming to an halt at some point. So I'm not going to go into details, but just to tell you that some of these terms, you can see that the term on the left is all related to u, which is the velocity of the flow. U and V are the velocity of the flow in the x and y direction. And then on the right side, you can get different resistive forces due to the pressure of the flow itself, and then the earth pressure coefficient here. And then this last term here, which is pretty important, that's what we call the resistive stress. And the resistive stress is going to be related directly to the rheology that you want to use. So maybe you guys talk about rheologies already when last week when you talk about lava flows. So it's going to be basically the same rheologies we're going to use for PDC than we use for lava flows. They are a little bit different in the way that we don't really want to use viscous terms, because the viscous term is going to allow the flow to actually propagate on very low slope gradient, or even like a flat surface that is pretty difficult to imagine for a PDC. So the most common rheological laws are here. So one is a frictional law that we call the Coulomb, the Moore Coulomb frictional rheology, where you can have one angle or two angles phase. So you can see here we put this tau that we have here in x and y in equation 4 and 5, and we just show you the equation that we can use based on the rheology that you want to use. So if you want to use a Coulomb rheology, like frictional rheology, you're going to use this term here that involve an internal friction coefficient and a basal friction coefficient. I'm going to go back to that after. Like I said, the viscous term, viscous rheology is not really used in PDC, but you can take this Coulomb rheology and add a coefficient that's going to be proportional to the acceleration and velocity of your flow. So we call this the U square term. And you can see we just simply take the Coulomb equation here and we add this term here of U to the square. That's called the Volmy rheology. That is also used in snow avalanches, for example, and other type of flows, debris flows as well. Then we can have a plastic rheology where we're going to assume that the resistive stress is constant and is directly related, only related to the velocity of the flow. But we basically just say, okay, in the plastic rheology, this term tau is actually a single value in Pascal. So 3,000 Pascal, 10,000 Pascal, right? And you apply that constant value toward the entire simulation. So it's not varying based on the thickness of the flow. It's not varying based on the slope angle or the normal stress. It's a constant. So you can add, as the same as the Coulomb, you can add a square velocity term to this plastic rheology. And then you can have also a Bingham rheology that is used in lava flows, right? Lava flow simulations, where you have a plastic rheology that you add a viscous term to it. Again, this is pretty tricky to use that for PDC because you have this viscous term that's going to allow the flow to propagate on very low slope, so it's never really going to stop, and that can be a problem. So all these depth average models have actually the same governing equation. It's just a different rheology and also different numerical framework that is going to vary between models. So I put here 3 models that are available on Victor, so Titan 2D, VoltFlow, and IMAX. VoltFlow is not directly available right now because it needs Octave to work. So it's still a work in progress there. If you want more information, we can give you more information on that implementation of VoltFlow on Victor. Initially, it's running on MATLAB. So MATLAB is not an open source software. So we found a way to actually use it on Victor, but it's not totally ready yet for user usage. But we have Titan 2D and IMAX, and you can see here the differences in these 3 models based on the platform where you can run them, the numerical framework, so that's pretty important. So all of them are using a finite volume scheme, but you can see that they adopt different ways of like speeding up the computational load to actually get the simulation to run faster. For example, Titan is using this adaptive finite volume when it's going to refine the grid to actually focus on the area where the changes in the flow properties are more important. Wolfo is using a normal finite volume solver, and then IMAX is using a little bit more robust solver that is actually modifying the grid to allow the model to interact a little bit more with the change in slope or angle, for example, during like complex topographies. Rheological laws are various for each of the model. They allow you to select the rheology you want to use. And then the big thing with Voltflow and IMAX is that they can also have a two-phase model that, in contrast to Titan, that the two-phase is for the moment limited to a water phase and a solid phase. Both for Voltflow and IMAX, you can actually use a gas phase together with a solid phase. And so that's pretty good to simulate the whole range of pyroclastic density currents we were talking about before. IMAX is actually also using air entrainment and erosion into the code that Voltflow and Titan are not doing that. And then processing, you can use Titan as in using parallel MPI libraries to get the simulation to run much faster. That thing that you cannot do with the two other models. And then finally, digital elevation model, you can see that most of them are using GDAL, so you can use any format for your DEM in GDAL, but Voltflow is using this golden software surfer format that is pretty limited. So that's also something to take into account. Right, and then the last thing I wanted to mention is this more Coulomb frictional rheology we're going to use today with Titan, based on two friction angles. One is the internal friction angle and one is the bed friction angle. So the internal friction angle needs to be always higher than the bed friction angle for the rheology to work. And so the internal friction angle is the steepest angle that the upper surface of a pile of dry material, dry sand, for example, can make with respect to the horizontal plane it's resting on. So it's mostly related to the internal properties of the PDC, for example, grain size distribution and the type of components you have in your PDC, whether it's dense blocks or vesicular class like pumices, for example. You may want to change the internal friction angle based on that. And then the bed friction angle is actually the angle that the plane needs to be inclined so that a block of material here in yellow will start to slide downslope at a constant speed. So you can see that the bed friction angle will be directly related to the slope angle, right? And so they're going to be a particular angle where your material can start moving or can stop, right? And so this is actually linked to the bed friction angle. So the internal friction angle doesn't have a big control on the flow propagation, so it's not something that Titan 2D is really sensitive on. The bed friction angle is really the one you want to be careful on selecting, because that's really the one that's going to play a huge role on the mobility of the flow. So the rule of thumb is that the lower the bed friction angle, the more mobile your flow is going to be, right? Because you will allow the flow to be able to propagate on slopes that are much lower than normal. So if you want to simulate a flow that is only a few kilometers run out, you will want to use high bed friction angles. And if you want to simulate a flow that goes actually further than that, like let's say 5 to 10 kilometers or more run out distance, then you may want to lower that bed friction angle to actually get a more mobile flow. So that's what we're going to do right now. We're going to actually use Victor and use Titan 2D to simulate pyroclastic density currents using frictional rheology. So I'm checking there's no questions. So let's do that. So let's go to Victor, and then what you're gonna do, you're gonna go into the shared folder, Victor courses, and then spring 2025, and then you're gonna have a week 5 folder here. And you're going to copy and paste that notebook here called Titan 2D Merapy. So you copy it and you paste it into your directory here. Before you do that, maybe what you can do also, it's going to be better because it's going to have to be inside that Titan 2D folder. So you need to install Titan 2D, right? So what you need to do, you open a terminal, and like we did for the other model, you type Victor setup, and then you see Titan 2D is number 16 here. So you just type 16 and then press enter, and then it's going to install that Titan 2D folder here. And so, all right, let me actually do it. So then we can use, oh, okay, let me just, that, okay. So then we have exactly the same files, okay? Okay, so Victor setup, 16. So it's installing Titan 2D file. So you're gonna get a new folder here called Titan 2D, right? So if you open it, you have 4 files in there. Input.py file, the Titan 2D notebook, an R script, and then the Titan 2D executable. Right, so what you want to do, you want to add that new notebook that I was talking about before, which is called Titan 2D Merapy. So you're going to go into the shared folder, Victor courses, Spring 2025, week 5. You're going to copy that Titan 2D Merapy notebook into the Titan 2D folder, and you're going to paste it in there. Okay. And so now you can see that I have the Titan 2D Merapy. So that's the one we're going to use. So you can still use that original Titan 2D notebook here. This is an example with Colima Volcano. It's the same example that you have if you install the code on your directly on your machine. So you can actually go through that if you want. But today, what I want you to use is the one for Merapy Volcano, so called Titan 2D Merapy. So first thing you want to do, and I think we already told you that before, but you definitely want to look at the user guide. So there's a Titan 2D user guide. The link is like here, just below the start of the after cell 2 of the notebook. So you can click on that link, and it's going to open you that user guide here, the Titan 2D user guide made for the version 4.0.0. So we're actually using the last version on Victor, which is 4.2.0. Not some major changes in the 2 versions. So you can definitely use that user guide to help you running Titan 2D on Victor. The only thing I want to mention is that this user guide was usually made for VHub. That was the previous platform we used to actually run Titan 2D. So the interface, the graphical interface is not there, but you will see that all the parameters that are described in that user guide are included also in the notebooks that we're using today for Titan. Okay, so if you want to know more about all these parameters we're going to use today and all the input that you need to run a Titan simulation, strongly advise you to go through this user guide to know a little bit more about Titan 2D. And it's the same for all the other codes on Victor. You really need to first read some papers or a user guide or the documentation on the model before starting to use the notebook. It's really gonna help you. So we're gonna go through that together now. So we can do like we did for the other notebook. So we're just gonna use this run button here to run the cell and advance. So the first thing you want to do is import all the libraries you need for running Titan 2D. All right, so I got an error, so let me see. Probably need to run it again. It's all right, that's working. Okay. Then we're gonna load the path where we have all the libraries needed for running Titan 2D. You can go directly here. So this cell here, number 3, is just whether you want to do a cleanup, and then you want to create a GIF at the end. So you can just go through it, and then here, this is the main parameters that you need to run the Titan 2D simulation. So first, you need to upload your DEM. So here we already have the DEM of Merapi for you that is in the shared folder of all the DEMs. So make sure that your DEM is in a GeoTIFF format. That is one of the GDAL format for this to work. And then you got all the parameters here. You can look up for these parameters, but what I'm gonna focus on here is these parameters here. So there's two ways you can define how long the simulation is going to be. First is with the maximum iterations of the simulation. This is this max iter variable here, or the time. And I strongly suggest that you use the time because it's really difficult to know how many iterations you're going to need for actually the flow to propagate down the slope and then completely stop, right? And by the way, using the conservation equations that I was talking about of mass and momentum, your flow is never completely going to stop. You're always going to have very small velocities of like less than 1 meter per second. But the way the partial differential equations are written, your velocity cannot be 0. So which means that you're going to get very slow velocity for a while, and that's where you're going to be able to say, okay, now I know that the flow is actually not moving anymore. So you need to select here a value that is large enough. So then you don't want to stop the flow before it reaching like very low velocity. And you also don't want to put a value that is too high to not like waste computational time, right? So you need to go by trial and error. So this is in seconds. And you can see here, for example, for a flow that is about 3 kilometer, 4 kilometer. So this is a land scale here. 4 kilometer. I expect it to be about 3 to 4 kilometer run out. I'm using like a little bit more than a minute, right? So one minute 20 seconds, so 80 seconds. So basically, a couple of minutes is good for small flows, and then if you want to simulate flows that are much larger in volumes, so this is like only half of a million cubic meter. If you want to use larger volumes, I probably suggest that you increase that maximum time to at least 10 minutes, for example, so 600 seconds for a flow that is much bigger. But in the end, you will still have to run several simulations until you find the correct value to use. This is a visualization here parameter. XZMF is for ParaView. If you want to get like a snapshot of the simulation at a particular time. And this is here the parameter where you're going to say, okay, every 10 seconds, I want to create a snapshot. Okay, so I want to save all the flow properties and all the simulation properties during this interval of time. So you can put it like less than that. Be aware that the smaller this number is, the more storage space it's going to take on your directory. So make sure that you don't select something that is less than 1 second, because otherwise you're going to get so many files that it's going to take a large storage space. But here, for example, you see that I have a maximum time of 80 seconds, and I'm going to save every 10 seconds. So which means that I'm only going to get 8 snapshots of my simulation. So if you want to make a video, for example, of your simulation, you may want to decrease that to 1 second, so to get like one snapshot of the flow inundation every second. All right, the next cell is the numerical parameters. So there's this adaptive mesh refinement. So basically, it's this ability of Titan to refine the grid cells to smaller cells, so then it can focus on some area where the flow properties are changing very fast. So you can actually define how much refinement you want to do. So for example, here, this is a number of elements across the smallest pi axis in the beginning of the simulation. So it's going to take the smallest axis of your source area, and it's going to divide that into smaller cells 16 times. So the greater this number is, the more refinements you're going to get. So the more accurate your simulation is going to be, but also the slower your simulation is going to be. Okay, so generally you want to use a value that is around, between 15 and 30. If you want to go higher than that, it would be only if you have a DEM that is pretty coarse, and you want to make sure that Titan is actually seeing the cells that are in front of the flow, so then it can adapt the parameters of the flow more accurately. But that's going to slow down your simulation. So generally, a number around 20 is pretty good. And then you got this other parameter here that is how you want the order of your solver for the partial differential equation. So you got the choice between first or second. First, it means that the flow properties in one cell are gonna stay constant. Second means that you're gonna actually allow a slope of the values inside one cell, which means that you can actually have a decrease or an increase of the flow properties inside one grid cell to actually simulate more accurately the change from one cell to another. Again, the first order is faster, a little bit less accurate, but okay if you have a good DEM. The second order is actually slower. So your simulation is going to be slower, but you may want to use the second order if you have a DEM that is pretty coarse. All right, then after we're going to move to the material model, which is basically your rheology. Okay, so you remember we talked about the different types of rheology. So in Titan, you have the choice between 4 different rheology. The Coulomb, the two-phase Pitman Lee is for this one is for Lahars, so you don't want to use that for PDC. Then you have the Volmy sum, and then the Pouliquin Fautor. So the Volmy, remember, it's the Coulomb plus square velocity term, like a turbulent term added to it. And then the Pouliquin Fautor is going to be the Coulomb with a term that is actually changing based on the depths, the flow depths, and the slope angle. So you're going to allow the friction angle to actually change whether you're on a high slope angle or a low slope angle, and same for if you have a thick flow or a thin flow. So here we're using the Moore Coulomb with 2 friction angles, so the internal friction angle and the bed friction angle. So that's actually this value that we're going to play with. So for the moment, we're going to set it at 25 degrees, but we're going to actually modify that later on to actually see the effect that it has on the flow. Next cell is the source properties. So in Titan, you have the choice between 2 different types of sources. Either you can add a pile, which is going to be either a circular circular pile or so a cylinder or a paraboloid, which is like an ellipsoid in 3D. That's going to be on top of your DM. Okay, you actually don't excavate anything from your original topography. And so if you use a pile, you need to set up the height of your pile, the center of your pile. So this is the X and Y UTM coordinates, the radius of the pile, so major and minor radius, the orientation, and then whether you want your pile to have an initial velocity and direction. For example, if you want to simulate blast, that's where you're going to have to put a velocity and a direction for your pile. Or you want to decide to use a flux. So this time you're going to get something that is extruding the ground at a particular rate. So you can put the influx here, a value, and the start and end time, as well as the center of your flux, and then the radius. So similar to the pile, you can use a circular flux, or you can use an asymmetric flux. It's always going to linearly decrease from the top to from the start to the end. Okay, so it's a linear decrease flux. So generally, the flux is pretty good when you want to use different pulses of collapse. For example, if you want to simulate a dome that is collapsing at different time, or if you want to have a column collapse with different stages of collapse, a flux is good to do that. So you can add several fluxes, or you can add several piles as you want. Also, it's good if you consider that the source is going to be lasting for a long time. So for example, if you say, okay, the collapse is actually like more than 60 seconds long at the source, then you may want to use a flux rather than a pile. The pile is only going to collapse everything at once. So that's the two options here. I'm going to skip the discharge plane. It's just if you want to get that some particular flux, volumetric flux at a different location on the DEM. And then this cell here is super important because that's basically where we're going to put everything into that input.py file that you see here. So you want to make sure this is the case. You can see that my input.py here has just been updated. You see modified 4 seconds ago, which means that I actually put everything, all the parameters that I entered before into that input.py. And then you can select the number of threads that you want. So here we're going to put 4 threads. You can increase that if you want the simulation to run faster, but it's not going to change too much. So we found out that 4 thread is actually pretty good for running Titan on Victor. And then we're going to run Titan using that command line here. So you're going to see that it's going to open a new window here, and then it's going to create some new files. And then you want to wait for that little asterisk here to go away, right? So you can track the simulation inside this window here. You can see that the simulation started. It said, okay, executable location is here. My maximum number of thread is here. My DEM is this one. And then I'm starting with a pile with internal friction angle of 30, basal friction angle of 25, and then the simulation is starting here and it's showing you all the timestamp. So if you go down, you can check the progress of your simulation. You see here 42 seconds already simulated. You remember that I put 80 seconds, right? So I want to wait until it goes into 80 seconds. And then once it's done, it's going to create some new files that you're going to see here appearing on the left. So it should be pretty fast. You see that at each time step, it's giving you different information. It's giving you the time of the simulation in hours, minutes, and seconds. It's also giving you the volume, maximum height, maximum velocity, and then average velocity. So you can actually check if these values are correct. Remember that a PDC rarely go over 100 meter per second. That would be a very, very fast PDC. So that's a way of controlling if your basal friction value is correct. If you get something that is very high here in the average velocity, it may mean that your basal friction value is too low. And so it's actually you don't have enough resistive stress to actually simulate the PDC pretty well. You see here that my average velocity is decreasing now to 12 meter per second after 1 minute. So I'm almost at the end of the simulation now. And that's the other thing you want to check. That average velocity needs to be closer to 1 or 2 meter per second to actually say, okay, the flow is actually has actually stopped, right? So you see here after 1 minute and 12 seconds, I'm actually getting an average velocity that is very low, like 2.8. So that's pretty good. And then I'm gonna reach 1 meter per second here after when the simulation is done. So that's good. So now my simulation is almost done. So you're gonna see some new files are gonna be created here. Here we go in your directory. So you should have all these files here created. I don't have time to go through all these files, but these are output files of different things you can actually get. The one that we're interested in is this pile height record, which is like the footprint of your flow depth at each time step. So it's recording the maximum flow depth at each time step. Or you can also get the dynamic pressure, the kinetic energy, things like that. And you also have output summary here that if you open it, it's showing you, remember that we say we want to save the output every 10 seconds. So here it's showing you that these parameters after 10 seconds, the average velocity, maximum height, center of the center of mass of the flow, and then different types of volume, right? You can see deposited volume, real volume, etc. So you may want to check that output summary to make sure everything is correct. You can see, for example, that my average velocity started at 0 and reached about 50 meters per second here after 40 seconds, and then went down to less than 1 meter per second at the end. So that's pretty good. That means that my simulation time, my D time was maximum time, sorry, was pretty good, 80 seconds to actually get the flow to stop completely. Right. So then once it's completed, then we can move to the output. Oops, I just run it again, but that's fine. So here is a way to select, to tell you how many steps do you have in your simulation, and you can select a step. So for example, I'm going to put step 8 here, which is the last step, and you can actually plot the distribution of the flow depths at a particular time step. So yeah, because now it's running again, I will actually have to wait that it's finished to actually get the output. Sorry about that, but yeah. So, for example, if you want a distribution of flow depths at a particular time step, then you can select a step, a different step between 0 to whatever the maximum is, and then you can get that. And the other way of actually getting your the output is actually to run this R script here, where you're gonna get not only the distribution of flow depths at a particular time step, but also the footprint of the maximum flow depths at any time step. Okay, so this is this pile height record here file that basically we're gonna process into R to actually change the format, because the header is a little bit weird on this pile height record file, and so you see it's not a standard header for GDAL. So we're gonna process that that highlight record file to create an ASCII file that's gonna be in the correct format, and then we're gonna plot that to actually get the footprint of the flow depths. So maybe you guys managed to do that. I just need to wait for the simulation to stop again, I guess, to actually get the output. So I'll have to wait a little bit. If you run into an error, let us know. Titan 2D is one of these models that is pretty complex, so which means that it's pretty easy to actually get an error message if you don't exactly, enter the parameter that the code wants to, and so can be pretty tricky to actually get the code to work. So if you use that notebook and then the other one, the Titan 2D notebook on Colima, that you should be good. So what you can do in the end is once you get that ASCII file that is basically the flow depths, the footprint of the flow depths, what you can do is to download this ASCII file, and then you can plot it in any software you want, like Quantum GIS, ArcGIS. It's going to be in the correct format for you to plot it on top of some other files that you have on a GIS software. So if you want to, plot that on top of a Google map, for example, to see, the footprint of your simulation, you can do that as well. Okay, so while it's still running, I can show you the other codes very quickly, and then I come back. The other code that we have is called IMAX. So you can also install it with the Victor setup. So if you go here, you can see IMAX is actually number 7 here. This is not the Lava version that maybe you've used last week, but this is the granular flow version. So it's called this one, IMX S-Flow 2D version 2. There is a notebook that you can run for using IMX. Let me tell you, this model is more complex than Titan in the way that it's using a mixture of a solid phase and solid particles of different sizes, as well as a gas phase. It's also using a source that is a little bit more complex than Titan in the way that you can really create the source that you want with the volume that you want, and also it's going to directly interact with the DEM. So there's a lot more parameters in there. Again, before you use that notebook for IMAX, I strongly suggest you to actually look at that paper here from Mattia and Tommaso and Samantha on the code. This is a really good paper that is really explaining everything that IMAX is doing and simulating with the equations, and then some examples of some flow that, like some benchmark, and then also radial flow at Krakatau over water surface. So I mean, go through that paper before running the notebook. That's pretty important. And then, yeah, it's pretty long to run. It's about half an hour. The cool thing with this code is that you can also simulate PDC going over water, for example, and you can also simulate the gas phase of the PDC in addition to a solid phase. So you can really like get into more specific parameters that you may want to use if you want to get more information about the dynamics, the internal dynamics of the flow. Now it takes longer to run, and so yeah, that's the kind of output you can get. For example, that's Colima volcano, and this is what we call a granular avalanche. So it's concentrated PDC going into several valleys from the top of the volcano. So you can get a map of the flow thickness here. And another thing that IMAX is doing that Titan is not is also varying the temperature of the flow, so taking into account the temperature of the flow, both for the gas phase and the solid phase. So a bit more complex and maybe more realistic, but also takes much longer to run a single simulation. All right, so let me go back to my simulation here if it's done. Not done yet. Okay, all right. Yeah, and that's pretty much it. We also have, like I said, we also have Voltflow, but it's still a work in progress. So if you're interested in running Voltflow on Victor, let us know, and we can communicate by emails by showing you how to do that. But for the moment, it's better to use Titan 2D or IMAX. I can see now that the simulation is much slower. So maybe it's because a lot of people are actually using it. All right, so I just wanted to show you an output. So for those who have already run the first simulation, what you can do is at home is also play with this basal friction value. So you can change the basal friction value that is on cell 7 here. So instead of 25, you can put 15, for example, or 20. So you put a lower value and compare the map that you get, especially the one with the R script. So the footprint of the flow inundation, and you're going to see that when you lower that basal friction value, you're going to get a flow that is much more mobile, that's going to be able to overcome some obstacles in the topography, like some ridges and valley banks, and it's going to go much further down the slope of the volcano. So another thing that I didn't mention is that if you decrease the basal friction value, you may want to increase the maximum time of the simulation. So if I put that to 15, I want to go up to the maximum time here and change it to, let's say, 120, something like that. Okay, you want to increase that because your flow is more mobile, so it's gonna take longer to come to a stop, to a halt, right? Make sure that when you lower that basal friction angle, you're actually increasing the maximum time there. Okay, so now it's completed. So let me see if I can manage to get an output. All right. Okay, so I got my output. So you see that this is the final flow depth. So this is a pile height, but at the final time step, you can see everything is sloping down the volcano. Nothing is really deposited on these steep slopes here, and everything is going to be deposited at the bottom of the ridge here. And you can see that the thickest of the deposits are about like more than 10 meter thick. And now I'm going to do the same, but this time I'm going to run this R script where I'm going to be able to actually get the footprint of the flow depths instead of just the final ones. So you see now it's creating that pile colima. Well, yeah, we need to change the name. Pile colima ASCII. So that's basically your flow depths raster. So you can take that raster and then put it into ArcGIS or Quantum GIS for using it after. So all right, so now it's done the conversion. So now we can plot it. Okay, and you see, so this is shade of the DEM, and then you can see now the footprint. So from the start to the end, right, of your flow depths that are now reaching like 25 meter or more, especially at the source here, since we put a height of 30 meter. So you can save that, for example, and then go up and change the basal friction angle value to put it to 15, run the simulation again and see how much that changed, and you will see that the flow that were constrained in that valley here suddenly is going to be able to overtop that ridge here. So and flow into these valleys that are below that ridge. So just to show you how sensitive Titan 2D is to that parameter here, the basal friction angle. All right, I went over. Sorry about that. Any questions? No questions? Yeah, Jordan?
Hello. Thank you for that. Can you hear me okay, firstly? Not sure if my headphones are. Yeah, perfect. I was just wondering, with the source location, is there a way to change it? I might have missed it somewhere when you were going through it, or is it automatically set at the peak of the volcano?
Oh, what? Sorry. Which parameter?
The source, and there is a way to change the source. It's where you set the pile.
Yeah.
There's a point where you set the UTM coordinates of the center of the paraboloid, and that's where you change the source.
Yeah, so you can put
Okay,
it anywhere.
thank you.
Yeah, you can put it anywhere. You can put it like at the top of the volcano. You can put it on the flank. Um, just be careful of the dimension of your pyrite. So you know the minor and major axis are gonna define how big your pile is, and that's gonna also define the volume, right? So if you put a circular pile, it's gonna be just the volume of a cylinder, but if you put an ellipsoid, it's gonna be the volume of a paraboloid. So it's a little bit different. But you can basically set up the minor major axis based on what volume you wanna simulate, yeah. And you can put it anywhere on the DEM, yeah.
Okay, thank you.
Mhm. Same for the flux. You can also do the same for the flux. You have a X and Y coordinates, so you can do that as well. One question is, could you run the create GIF? No, yeah, it's not working for the moment. The GIF, sorry about that. We're gonna actually fix that, but the GIF is not working. Yeah, same. The code is working, but I have a problem with the create GIF. Yeah, sorry about that. Yeah, the create GIF is still not working, so yeah, don't use it for the moment. Yeah, you can actually make one yourself if you want. Once you get the different output files, you can actually just merge them together into one of the software of your choice to actually create a GIF. It's not going to look great right now because we selected it every 10 seconds, right? So it's going to look a little bit weird. If you want to really make a nice video, like the one I show you on my first slide, right? You may want to select the D time to be 1 second, something like that. So then you get like, one file every second, and then you merge all these into a GIF. Yeah.